So we start with the last chapter today. It's a chapter about the eigenvalues and eigenvectors, or I call it, I call it with this fancy name, spectral analysis of matrices. I call it. It's a legitimate name of the things we're going to study, even though probably we're not going to go that deep into this area. Those of you who will continue your mathematical development in the second year, you will learn a lot more about spectral analysis, but this last chapter in this particular topic, it just gives you some brief overview, what happens there, what kind of tools we have, and what they're good for. So I start with the regular metrics, and spectral analysis is done only for square matrices. So we look at the square matrix, you see size n times n. I assume that my matrix has scalars from the field F. I just remind you that F, as usual, it's either real numbers, rationals, or complex numbers. And here comes the first definition of the spectral analysis. A scalar from your field of scalars, F, you call it eigenvalue. You call it eigenvalue if and only if. That's the way you spell it, and that's the way you say it, eigenvalue. If you can produce a vector, n-dimensional n-tuple of scalars, vector x, subject to the following two conditions. One of them, it should be non-zero vector, and the second condition, the relation between the vector x and your matrix A and the scalar lambda is like this. If you apply your matrix to the vector x, the result of the application is simple scaling of the vector x. So if the vector is such that the action of the matrix on that vector is a simple scaling by the given scalar lambda, in that case, this scale is called the eigenvalue, and this vector x, which you were able to produce, is called the eigenvector associated with this value lambda. And of course, this pair of objects, eigenvalue and associated eigenvector, they associated with the matrix A, because that's the link. That's the link between the eigenvalue, eigenvector, and the matrix A. So it's a triple of objects. So every matrix may have this couple of eigen things or spectral things. It's a fancy name, but still, eigenvalues and eigenvectors. So our job will be to find out the ways how we can identify these eigenvalues, how we can identify the associated eigenvectors. You will learn very soon that basically we have every tool we need for that. We just have to rearrange the tools a little bit differently, just change the angle or point of view at the things, and you will see that the tools, the machinery which is needed to finding these eigenvalues and eigenvectors, we have with this machinery. The other thing you will learn a little bit, why we need these things, what they are good for, but that's the second part of the chapter. First, we need to study the machinery, how to find these things, how to find these things. Now, there is another term which is associated with the same couple of objects, and in order to present that, I have to give you a chain of implications like this. Look at this. If I take this identity, which is a key identity which connects eigenvalue, eigenvector, and the matrix, if I take this identity like this, I can claim this. This identity is equivalent to saying, if I just take this right-hand side and move it on the left-hand side, that's how it will be. Now this left-hand side has a common factor x. If I factorize this left-hand side now, given that we're just dealing with matrices, that's how the factorization will go. This is equivalent to the following thing. Look at this. I factor out x. The remaining bits are like this, matrix A, and here, even though I didn't have any matrix, I can insert identity matrix of the appropriate size, In. That's how it will be if I factor out x. And then, what can I say? I can say this is a matrix, right? A was originally a matrix of size n times n. Identity, it's another matrix of size n times n. Combination will be third matrix of n times n. And the vector x is such that it vanishes the matrix. For such vectors, we have a name. For the collection of such vectors, we had a name. We call it a null space of a matrix. Or the kernel of the matrix. So equivalently, I can say that X comes from the null space of this particular matrix. So you can just produce this alternative for the definition of the eigenvalue. Here's my alternative. Scalar lambda is the eigenvalue if and only if it is the eigenvalue if and only if this set, and this symbol E sub lambda is just my notation for this set. It's a standard notation. Yellow Book uses this notation heavily, so it's worth remembering it. So if this, and I said set I should say in fact space or subspace in fact, because we all know that the null space is a subspace, a proper subspace. So the lambda value is the eigenvalue if and only if the associated subspace E lambda, which will be called eigensubspace, if the associated eigensubspace is non-trivial. If there is something in this subspace which is non-zero, you see, remember here the definition was sitting around this piece. Lambda is eigenvalue when you can produce a non-zero vector, which makes this happening. Equivalently now, or alternatively now, we say that lambda is the eigenvalue when the associated eigensubspace, which is a null space of this matrix, has something non-trivial in it, something which is non-zero, something non-trivial in it. That's another definition of the eigenvalue. Quite legitimate definition, and I'm going to use it from time to time.